All right, so for example number 6, we have a bunch of data. So I'm not going to write all of it down. I'll just write a couple things down. But if you look in your book on page 211, so crack open your books to page 211, there's like a table of values. And the table of values is years since 1900. It's the population of Alaska. Okay? And so, like, in 1920, Alaska had like 55,036 people, according to census data. And in 1930, they had 59,278. And then if you go down in the year 2000, which is 100 years later than 1900, they had 626,932 people based on U.S. Census data. And so what the textbook wants us to do, God bless you, they want us to first find a logistic model. We'll talk about that when we get to it. Part B, when we find the logistics model, the next thing they want us to do is predict the population of Alaska in 2020. Part C, they wanted us to find the point of inflection. There's some complicated math for that. And then part D, what they wanted us to do was to determine the long-term growth. So I'm going to write it a little different in your book. Your book uses the terminology long-term growth. I'm going to rewrite it as find the limit to growth. And we'll talk about that when we talk about logistic models. So what they've done, here's a scenario. Mr. Adams has been hired by the state of Alaska to answer all these questions. And they said, here you go, Mr. Adams. Here's our census data for the last 100 years. And here's what we need to know. We need to know how many people we're going to have in 2020 so we can plan. We want to know when did we have our highest growth rate. And, you know, so they need this information for planning for the entire state. So I say, all right, give me the data, and then I would go through this process. And they said, well, here's the thing. We would love, we don't have 1 million people. We want to try to accommodate at least 1 million people in our state. So maybe they figure if they have 1 million people in their state, it'll generate a certain average tax revenue from 1 million people, and maybe that's a goal, right? Maybe they want their state to grow. And so they come to me and they ask me all this information. I say, all right. So the first thing I need to do is a model of population growth. So the first thing we need to tackle is this logistic model. And so to tackle, now the reason they call it a logistic model is it's a special type of equation. It looks like this: y equals c over 1 plus a times e raised to the negative b of x. All right. Now x is sometimes written as t, but it refers to time. And y is going to be the population in this case. Now what this looks like graphically, if I were to, and I'm just going to sketch it kind of freehand, normally we only look at quadrant 1. And so the way that the model looks is it normally looks like this, with some sort of horizontal asymptote. Now that horizontal asymptote is usually equal to the number c, and in mathematics we call that a limit to growth. And so the logistic model looks like this, and then this would be what we call the initial condition. What did you start off with? How many people? And almost everything in any type of ecological system or model, there's a growth rate. So in 1900, they had 55,000 people. Well, of those 55,000 people, you would guess that they had approximately 25,000 couples. And so of the 25,000 couples, they produced, on average, 2.2 children. So the 55,000 grows to 60,000 and then 70,000. But then sometimes people move away. They go off to college. They get a job in New York City because they've always wanted to live in the big city because they hated growing up in Alaska because all they do there is fish and stuff like that. And some people love being in Alaska. And there's some people from New York City that hate New York City because there's a bunch of traffic. So they move to Alaska to get away so they can do fishing. And so you have all these reasons that people come and go from Alaska. And what that does is that gives us this information here. But there's a growth rate. As time progresses, they get more and more people. It's kind of exponential in the fact. It's kind of exponential in the fact that up till about this point, it almost looks like an exponential growth. But what limits growth are the resources. Okay, so I'll give you the predator versus prey model, and then we'll try to apply it to human beings, because obviously we're at the top of the food chain. But in most closed systems, if you're a smaller animal, then you're probably prey. And so you can grow and grow and grow, but the predators are going to, well, eat you. It's kind of gross, but you're limited in how many predators there are. And the other thing are resources. So if you're prey and you're in the middle or the bottom of the food chain, you can only consume so much. So there are a lot of parameters that regulate what your growth could be. Now for human beings, it would take a long time from now, but Earth is only so big. And so we can only have so many people on planet Earth. Think of this classroom. I could have probably had only 5 students in the AP Calculus class 40 years ago. But over time, parents said, well, why don't you try it? Over time, more and more kids signed up. But we know that there's a limitation to the number of children that will fit in this classroom. So there's something that limits the growth. So what we have is we have some sort of exponential growth where each year it increases by a certain number, but then at some point it starts to cap off. And in Alaska's case, it might cap off because, well, it's really cold there. So maybe some people don't want to live there. There's only so many resources there because of the environment that they're in. So they may have a cap. More than likely, it's probably economic growth. They only have so many jobs in Alaska. And so they might be interested in increasing the limit to growth. We saw this during the recession. Well, here locally, Niles was a pretty big, at one point in time in like the 80s, they had like a lot of companies that actually manufactured things. And during the recession, most of those companies went out of business, and what the people had to do is move to South Bend. So that they tried to get jobs in South Bend because there were more jobs, and so some of those families moved. So they had a limit to growth based on economics. Okay? This could be a case for Alaska. So now, I got to figure this out. Now, to do a logistic model, we can do that on our calculator. So if you come and everybody turn your calculators on and go to Edit, go to Stat, hit your Stat button and go to Edit. And I need for you guys to clear out your L1 and L2 and put this data into your calculator, and I'll give you a few minutes to do that. The first column, L1, represents the years since 1900, and this is in your textbook on page 211. So the first column is 20, 30, 40, 50, 60, and so on, all the way up to 100. And if you can't see the screen in the back, like I said, it's on page 211 in your textbook. L2 represents the population at that time. All right, so here's what we got. Now that we've got this stuff entered in, okay? Now that we've got it entered in, we need to do the regression. So follow along with me, okay? Down here, it'll show what buttons I hit and what number they're in. All right, so I'm going to go real slow. We want to graph this. So I'm going to come in here, and I'm going to clear out that first equation. because that's where I'm going to save it. So I'm going to hit stat again.
Stat.
So let me clear this. I'm going to hit stat. Wait, let me clear this one more time. And so you hit stat. That's the first button that you hit. Then if you hit the cursor to the right, you'll get the calculate menu. Then if you come down, on my calculator it's option B. On some of the older calculators it might be like option 8. But you want to come down until it says logistic. Okay. Is everybody at logistic?
Yeah.
Okay. So now what we're going to do is we're going to hit enter. Now on some of the older calculators it might look a little different, but what's it saying is where do we get the x values from? L1. Where do we get the y values from? L2. Now some of you guys it might not even show that. You have to enter that in manually. This is the default. Frequency list, we didn't do one. There you might put like L3, but we didn't do one, so you can leave it blank. Now to store it, I want to store this equation. So it's going to write an equation that looks like this, and I want to store it in y1. So now to do that, if you hit vars, which is really variables, then you scroll over one to y variables. It's a function, so I'm going to choose function, and then I want y1. So when I do that, notice that I have y1 right here. Now if you have an older calculator, you could still do that. You could still hit y1, you go through the vars, put y1, and then hit enter, and then it will still store it for you. Now I'm going to go to where calculate is highlighted, and I'm going to hit enter. And then it says 83 logistic L1, L2, comma, Y1. And then it's done. Now what it's doing is it's giving me the A, the B, and the C value. So I've just found my logistic equation. My logistic equation is y equals, then you list the C number, which I kind of took off the screen real quick. My C number is 895,597, so I'm going to say 895598 all over 1 plus A. A was 71.57 approximately. 71.57, which is times E raised to the negative B, which would be 0.0516 times X. Now, your textbook probably raises that to T. Actually, it raised it to X. But a lot of times we would leave that as T, because that usually represents the time, right? But our calculator doesn't have T easily accessible, so we'll just say X, right? So what did I do? I made a mathematical equation that I could plug in the year, which is my X value, and then it'll calculate the population. All right? Now, this stored it in Y1. Okay? So that's the equation in Y1. Don't worry about Y2. We're going to get to that in a second. So let me turn it off. Now, what we need to do in order to graph that thing, 2020 is 120 years from 1900. So now I need to set up the window so I can see the graph. Okay? So my X value should go from 0 to 130. I want to go a little bit before and a little bit after. Does that make sense to you guys? Set up your window this way. So click on your window button. Okay? And then we want X-min to be 0 and the X-max to be 130. Okay? You guys there? All right. So now the other thing is that what is our Y minimum value? Well, actually, it should probably go down to like, our minimum value was, what was the first value we had for a population? About 55,000. Here's the problem. If I put a Y minimum value of 55,000, when you graph it, you can barely see the bottom of it. So I'm going to go kind of symmetrically below, right? The maximum value will be the limit to growth, which is about 900,000. So my Y max is 900,000, but so I could look at the graph and kind of see it more clearly, I'm going to do negative 100,000 for Y. I don't have to, but I'm going to because you'll see when we look at the graph why I did that. So we'll just barely be able to see the x-intercept or the x-axis. All right. So does everybody have this in their thing? One other thing I want to do, we've plotted the points, so let's make sure our plots are on. So if you go to second y equals, then and make sure plot 1 is turned on. Mine's turned on because I did this last hour, but I just want to make sure that it has L1, L2, so it's turned on.
Wait, do you want it to be a dot plot or?
It doesn't matter. You could do dots, you could do crosshairs, I don't care. Now hit graph. And when you get a graph, you should see something that looks like this. Now, my little blue boxes, some of you guys probably have crosses or dots or whatever. They should be pretty close to the line. It's not every dot is right on the line, but they should be close. Now the red line is our logistic model. It's this equation, okay? So this is part A.
Adams?
Yeah.
My calculator didn't graph the points, you just graphed the line.
You got to make sure your plot's turned on.
It is.
It should check the plot. Give it here. Oh, we'll fix it. You've got a different menu thing on your screen. We'll fix it. When we're done with the video, I'll show you. We got to turn that off.
Okay.
You have like a program that shows your display a little different than the way the calculator is normally set up. It'll just take me a few minutes, but I'll show you that afterwards. All right. So for part B, we needed to predict what is the population in 2020. Now, how many years is that after 1900?
2.
Yeah, it's 120 after
Oh, Jesus.
1900, right?
I thought it was like
So what x value are we looking for? 120. Is that right?
Yeah.
So now there's a couple of ways to do that on the graphing calculator. If I hit trace, now here's the weird thing. If I hit trace, look in the upper left-hand corner. What does my calculator say?
L1, L2, P1.
Plot 1. Do I want to trace the plots, the data points, or do I want to trace the function? The function. So what I'm going to do is I'm going to hit my cursor down, and that allows me to scroll through the different things that are being graphed. Did you fix it? Okay, good. So now that it's blinking, and I'm on the right function, if I just enter in 120, whoops, I got to hit it, 120, and I get this x equals 120, when I hit enter, it'll automatically find the point on the line where x equals 120, and it'll spit out the corresponding y value. So I hit that, boom, 781,253 people.
Yeah.
So based on the current logistical model, in 2020, that you would expect 781,000 people in Alaska. Now, it may not be that much, right? We can't predict the future, but it's a good ballpark. Okay? If things don't change too much, right? That's only like 6 years away, 5 years away, right?
That's
Yeah.
scary.
Okay. So now, what does that mean? When x equals this, y equals 781,253. Well, that's the population in 2020, approximately, estimated. So we should say estimate population. Okay? That was part B. Part C says find the inflection point. What? What? Okay, so C says find the point of inflection. And so remember, I've got this graph that looks like this on my calculator. What's the point of inflection? Does anybody remember?
Where it changes the
The concavity changes, right? So now if I look at the beginning of this, the concavity, and this is related to f prime, right? So f double prime of x is positive. That's how I get this concave up business, right? But then as I look at the end here, f double prime of x is negative. And that's how I get this concave down. So at some point in time in the middle here, somewhere I have a point of inflection. And this occurs when f double prime of x equals 0, right? Is that right? Now, why would they ask that? Does anybody know why? Let me give you a clue. My function is increasing when we start off, which means that f prime is positive, right? That causes my function to increase. But then, as we get to the end, I don't want to say that it decreases, because it kind of levels off, but it doesn't increase as much. Does that make sense?
Yeah.
And that's based on the concavity. If you're increasing but curling down, you're going to increase at a much lower rate. So here, we've got f prime of x is really positive. Here, f prime of x, well, it's just a little bit bigger than 0. So it's barely positive, right? It's a small positive sign.
Barely.
Barely. Right? So it doesn't increase much. So at the point of inflection, just prior to the point of inflection, that's when it has its highest rate or increase. Highest increase rate. Because that's when the slope's the steepest too, if you look at it. Right? If we were to look at the tangent lines, so if I look at the, if I were to do a tangent line here, right, like this represents f prime, right? And then I do another little teeny tiny tangent line here, that's another f prime. Well, right here, it's the steepest, right? And then as I do the tangent lines, it becomes less and less, right? And that's all based on f prime. So now if I were the governor of Alaska, if I figure out where this point of inflection occurs, that's when we had our highest growth rate, around that time, whatever year that is. And so I might want to duplicate that, right? If I wanted my population to grow, I might want to figure out what happened. So that's why the point of inflection is important. Does that make sense to you guys? Maybe they opened a new business, or maybe there was a new hospital, or who knows what it is, but I need to start there. Does that make sense? Well, now how do I find the point of inflection? Well, the point of inflection occurs when f prime of x is 0. Well, that's not a problem, right? We're just going to come in here and we're going to say, all right, y is 895,000 approximately. What is it? 95. Tell me the rest of the numbers.
597.
597 all over 1 plus, what was the rest of it?
71.5.
71.5 times e raised to all this stuff, right?
Negative.
So it's 71.57 e to the negative 0.0516 to the x, right? Okay, cool. I did that. Why don't you guys just take the derivative of that and then take the other derivative? So give me y double prime. Ready? I'll give you 30 seconds. Go.
Yeah, right.
Oh wait, what's the problem?
It's super big and complicated.
It's super big and complicated,
Wait,
right?
Is it 0?
So yeah, and then once you get y double prime, remember we want to take y double prime and then set it equal to 0 and then solve for what x value, which is trapped in the exponent. What x value makes it equal 0? Is that easy?
No.
No. Boy, I bet you guys would love for me to show you how to do this on your calculator.
Yes.
And drive.
Or just do it.
Okay, so you guys ready? Watch Mr. Adams. I'm going to hit second, catalog. Now here's the problem. N derived starts with the letter N. I'm on the A's. I'd have to scroll through about 50 commands. But if you look above the log button, there's a green N. Hit the log button, and now we're in the N's. You're welcome. So now I'm just going to scroll down 2 or 3 times and get N derived. You guys with me?
Yes.
Move on to the next step? Yes? All right. So we're going to hit that in. Now that's the first derivative, but I want the second derivative, right? So I'm going to take the derivative of a derivative. Normally I want to plug the function in, or the expression. This would be like x cubed or whatever the function is. And then I want to let the calculator know, take the derivative with respect to x, and then I want it to calculate a value at a value.
And the phones are working, so we are up and running. Thank you for your patience.
Well, that's good enough. So I want to take the derivative of a derivative, but I want to graph it. So here's how you do that. I'm going to hit N derive again, so I'm going to hit second catalog, hit the log button because the letter N is there, and then go down to N derive. So I'm taking the derivative of a derivative. Well, what am I taking the derivative of? Y1. So now I have to hit vars, go to y vars, okay? Then if I hit enter, I have to hit function, and then I hit y1. Is that in there?
Yes.
So I'm taking the derivative of y1 with respect to x. So I hit comma x. Somebody has their hand up, yes?
Mine looks a lot different. Mine's like a newer one.
A what?
Mine's like a newer one, so it has D over D, and then you're supposed to put X.
Go to your mode and put classic. Right now you're in the math type. If you go to your, yeah, you've got like DDX, right? So yours would look like this. Zach, you could change it to classic, or you could do like D, DX of D, DX, and then in parentheses you would put Y1, and then you would put, I think it's X, and then X. And then you have to put an X and an X here too. But if you just go back to the other menu, it'll be better. So now I want to take, now here's the thing, is I'm telling my calculator, at this point I got to tell it what number to plug in. Well, I don't want to tell it a number, I'm going to tell it X. So I'm going to say, I'm going to let the calculator choose a number for X based on what we put in the window. Well, that's fine for that function, but remember, I want to take the derivative of a derivative, and so now I've got all this right here, that's plugging in the derivative of the first function. So now I've got to hit comma x, because everything's going to be of x, and then the same corresponding x value. Okay? Does that make sense?
No.
Plug it in the way you see it on the screen. Okay? Now what that does is it's going to tell the calculator, take the derivative of y, and that'll spit out a corresponding y value. And then it says take the derivative of that. So we're taking the derivative of x values as they line up with the graph. So it'll do like x equals 0, x equals 1, x equals 2. And then it'll graph the x and y values on the graph. So, when you're done, does everybody have this on their screen? We're going to see a very small line. You'll barely be able to see it, but it's the second derivative. See that little green line on my screen? That's the graph of the second derivative. Now, we are doing a lot of work. Why are we doing that? What are we trying to figure out? Point of inflection, which occurs when what?
The
Concavity switches from positive to negative. Now, if I were to, so point of inflection occurs when y double prime equals 0. The green line is the graph of y double prime, right? So how do I figure out when that green line equals 0?
The table,
We could do the table.
or you could trace it.
Like the zeros.
Yeah, or we could find the x-intercept, which is the 0, right? There's a command for that. The problem is that I've got a really big x value, and this is where we ran into a little trouble the second hours, because we knew the answer, but I was trying to figure out an easy way to explain it. So basically what we're going to do, looking at my red line though, where would you suspect that the point of inflection occurs?
Right about in the middle.
Yeah, right about here, right? Somewhere in here. So let's figure out what this x value is and set the window a little bit before and a little bit after. Does that make sense to you guys? Okay, so what I want to do is I'm going to hit trace again, and in the upper left-hand corner it says plot. Now I'm just going to leave it there, and when I hit the right button, notice that it just toggles from one data point to the next, and that data point is when x equals 80. So we know that the point of inflection is somewhere around x equals 80, which means this green line, which by the way, by looking at the graph right now, I can't tell where it crosses the x-axis. The only thing I know is it's around 80. Does that make sense? So what I need to do is I need to figure out how to zoom my window in around this green line and then figure out where it crosses x-axis, right? Does that make sense to you guys? And that will tell me what value of x makes y double prime equals 0. You guys with me so far? Okay, so what I'm going to do then is I'm going to change the window. So I'm going to go to Window, and so I'm going to plug in my minimum x value is 70, my maximum x value is 90, because 80 is right in the middle. Now here's an interesting thing. What should I set my y min to?
You
need to see where it comes. So something small.
Yeah, it's got to be close to 0. So I
One,
see some people
negative
put in, but it should be -1, right? Yeah. Something like this. So I could just put -1 and 1, right? Because I want to see when it crosses and I get y equals 0. Does that make sense? So I'm going to draw a little window. Well, let's just graph it and see. Now this will take a really long time because it's got to graph all those red points, right? That red line, which is like 700,000, 600,000, really big numbers. And so most of your calculators will have this little thing that spins. The older calculators, it just kind of flashes up here. It's going to take a while. And then what it'll do is it'll graph the green line, and we'll be able to see exactly where it crosses the x-axis. Okay? Now you could speed this up by going into your y equals menu and turning off y equals 1. Do you guys know how to turn them off and on yet? Have I shown you guys that? I'll show you after this. Well, now we have to wait.
If you hit second on, it stops.
Yeah.
Yeah.
Thank you for that little tidbit of information. All right, so here we go. So the green line's graph, because that's easy. It's still calculating the red graph. So I'm going to turn that off to save me some time. So what I'm going to do is if you go into y equals, if I move the cursor until the equal sign is flashing and I hit enter, and if I just move down, see how this equal sign is highlighted in black and this one isn't? That means that y2 is turned on and y1 is turned off. So now if I hit graph, it'll go a little quicker. Not too much quicker, but it'll go quicker. Okay? The reason I turned it off, though, is because when we go to plot for the 0, it'll take a really long time if we have that y1 turned on. It'll take like 5 minutes. It'll give you the right answer. Okay? And so we just have to wait patiently. What we could do, though, is remember that this is 70, so this is like 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, and 83. So that my number is between 82 and 83. Okay? Now, I could verify that if you hit trace, We have to wait, it's still not quite done. If you hit trace, I've got the plot, and then if I hit down, now the only thing it shows is the green one. That saves us a lot of time. So now what I want to do is I want to find the 0. So if I hit 82 and hit enter, it still doesn't quite show up on the screen. So if I go a little bit to the right, a little bit to the right, as I get closer to 83, you can see that it gets close to 0. So now if I hit second trace again, and option number 2, I can calculate the 0. I'm a little bit to the left of the 0. Now I'm going to go a little bit to the right of the 0, but you can't see it on the screen, so I'm going to hit enter. And then to guess, I'm going to come back. And then I hit enter, and it'll tell me, and it's about 87.2 or something like that. And it'll take a long time. So it's like 82.75, which will round up to 83. Now what does that mean?
That means that the point of concavity is that point. When I do myself to do that.
That means when x equals 83 is when y double prime is approximately 0. What that means in regular English, though, is that in 1983, Alaska was at its highest growth. Okay? So that's part C. Part D wants us to figure out what the limit to that is. So to find the limit of that, so part D wants to know what will the growth look like over the long run. So they say long run. Mr. Adams said because it's a logistic model, it's a limit to growth. Okay, so that's always our C term. That means my population will never really be bigger than that. Now the reason for that is I've got 895,597 all over 1 plus all this other stuff. Now all this other stuff will never be negative. In fact, the only thing I can hope for is that it will be very close to 0. So as my function approaches infinity, the very highest value that I can have for this function is this 895 thing. And then we'll double check that graphically too. That's the highest it'll grow because the denominator, the smallest I could get that number is 1. Does that make sense to you guys? Because I'm adding a positive number. And yes, it's raised to a negative power, but remember, that's just a fraction. So if I look at this graphically now this is where we're going to have to change some things on our calculator. What I could do is I could go to my window, right? And there it is. I could plug in, I could look at the end behavior. So I'm going to come back here, and I'm going to turn my original function on. I'm going to turn my derivative off, and I'm going to change the window. Now I know, pick out a really big number for your x value.
1 million.
No, not that big. Like 10,000 would be a good number, right?
10,000.
That would be 10,000 years from now. We could even choose 1,000 years from now. So if we choose 900 to 1,000, and then now my y value would change a little bit. I'm going to plot, I think, 700,000 to 900,000. because I don't think it'll be any bigger than that. And now I'm just going to hit graph. And so what I'm going to do is I'm going to hit trace. I'm going to come down, and at 950 years from 1900, which is like, what is that, like 2800 or something like that, 2850, we're going to have 895,597 people.